All right, before we talk binomial probability, we're going to do a little bit of a review of some probability topics, just some of the basics. This is a little bit because we're just coming off spring break, but also because we've been working on probability for a while, and I don't want you to lose track of some of the things that we may have discussed early on. One of the things is the idea that there are two different types of probability: theoretical probability and experimental probability. And theoretical is where we've spent most of our time. That's what should happen, and it's calculated. We just look at the numbers and decide, well, calculate, I guess, what the theoretical probability for a situation will be. Experimental probability is a little bit different. That's maybe we can't really do theoretical, or maybe we don't want to. Maybe we want to do an experiment and see what happens. And so we actually perform an experiment or an activity. And when we do this, what we come up with is the experimental probability, and that can also be called relative frequency or empirical probability. All three of these terms mean the exact same thing: experimental probability, empirical probability, relative frequency. They all mean the same thing, that we did some kind of experiment or activity to come up with our probability. Simulations would fall into this category because even though we are simulating the activity, we are actually performing an activity to come up with our numbers rather than just using the theoretical probability. And theoretical probability leads us to the most important thing about probability. And I'm sure you all remember this one, but just to make sure, probability is successes over outcomes. When we're asked for the probability for some event, what we're looking for is how many successes are there, how many outcomes are there, and probability is successes over outcomes. That's our single most important thing about probability. Anybody have any questions about any of those ideas before we do turn our attention to binomial probability? Okay. One example of binomial probability is flipping a coin. When we say binomial, what we mean is there are only two outcomes in one single event. Like flipping a coin would be a binomial probability event because there are only two things that could happen: heads or tails. We've talked about with our tree diagrams before, where if you were to have a baby, it's boy or girl, two outcomes. And there are other examples, but basically that's the idea behind binomial probability, is those are going to occur for us when there are only two possible outcomes. Now, we might do the thing more than once. Like here, we're going to flip a coin, but we're going to flip that coin 3 times, or we're going to flip 3 coins, which is the same as flipping a coin 3 times. And we want to find what's the probability of getting exactly 2 heads. Really important in this section of section 7.4, the binomial probability stuff, is the difference between the words exactly and at least. We saw that when we did our tree diagrams. Exactly means no more, no less. At least means at least. It could be this or more. And so here, we're looking for the probability of getting exactly 2 heads when we flip 3 coins. And you might think we could do this with a tree diagram. You could. I'm going to draw this. I don't want you to. And you'll see why in just a minute. We could do this with a tree diagram because when I flip that first coin, I could have heads, tails. And then the second coin would be heads, tails. And then the third coin would be heads, tails. And what happens is when we get into tree diagrams that have several different columns in them, it gets messy. And so I don't think I would go with the tree diagram for this, although you could. If you do, you want to make sure you leave a lot of space and draw it really big. Instead, we're flipping a coin and we're flipping 3 coins. And when we do this, how many outcomes are possible on the first flip? How many outcomes are possible when I flip that first coin? And I promise there's no trick questions. That's right, Carolina, there's 2. How about the second coin? 2. And how about that third coin? 2. Awesome. Perfect. I got all kinds of 2s. That's great. So we have 2 outcomes on the first coin, 2 outcomes on the second coin, 2 outcomes on the third coin. Always nice when we can lean back into something we did before. The fundamental principle of counting tells us find the number of possibilities for each stage of the problem and multiply those together. Be careful. 2 times 2 is 4, times 2 is 8. So we know we're going to have 8 total outcomes here when I flip these 3 coins. Well, 8's not that big a number. If I only have 8 outcomes, I'm going to just write down my sample space. So let's see. When I write down my sample space, I could get all heads. I could get 2 heads and a tail. I could also get 2 heads and a tail with the tail in the middle. And I could get 2 heads and a tail with the tail at the beginning. Let me know if you have any questions about what we're writing down here. It's important for me to know that you're okay with these being different from each other. And if you think of this as being 3 coins, it's a penny, a nickel, and a dime. Well, here the dime had tails. Here the nickel was tails, and here the penny was tails. And that's how those are different outcomes from each other. I could also get 2 tails and a head. I could have tails, tails, heads. The heads could be in the middle, the heads could be first, and then I could have all tails. I knew I was going to have 8 outcomes here because the fundamental principle of counting told me so, and I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, those are my 8 outcomes. Now, back to the question. And the question said, what is the probability of getting exactly 2 heads? What is the probability of getting exactly 2 heads here? Remember, probability is successes over outcomes. What's the probability of getting exactly 2 heads? And it's okay if you're a little rusty coming back off spring break. I'm feeling that too. It'll take, a little bit of time to shake that off. That's okay. Excellent, Lorraine. Genesis, very good. We can see probability is going to be successes over outcomes. And so let's see. Well, I knew there were 8 outcomes, so I'm definitely going to have an 8 in the denominator. And then my successes are going to be where I have exactly 2 heads, no more, no less. And when I go through and I try to find those, well, that's 3 heads. That has 2 heads, 2 heads, 2 heads. That only has 1 head, 1 head, 1 head, and no heads. So the successes, the ways I can get exactly 2 heads are these 3 right here. So I have 3 successes and 8 outcomes. So the probability of getting exactly 2 heads is 3 out of 8. Writing down the sample space when it's small like that is not a bad way to go at all. If you're thinking, but I don't want to write the sample space. When we have a binomial probability situation like this one, we have another way we can go, and that's what we're going to look at next. Excuse me. Okay, remember, binomial probability, this is only allowed when there are 2 outcomes for one of our events. So we're flipping a coin, heads, tails, that kind of thing. There's only 2 things that can happen on one of the flips or one of the events. And what you'll see over here that's new is this triangle over here. If you happen to know what that's called, that's great. If not, that's perfectly fine. Anybody know what this triangle is called? Very good. Outstanding. Genesis, Lorraine, terrific. You're exactly right. This is called Pascal's triangle. And then, if you've seen it before, that's awesome. If you haven't, it's totally fine. We're going to talk about it. It's named after Blaise Pascal, who was a French mathematician in the 1600s. And we're going to see how this gets put to use here in just a second. But it's important to know it's called Pascal's triangle. And as far as, well, where the heck did all those numbers come from? I think that's a perfectly reasonable question to have at this point. So as we look at this triangle, we start out with row 0. It just has one number in it. And row 1 has 2 ones in it. Neither one of those is that interesting. And then the way this triangle gets built is you can see there's ones all the way along the outside edges. Those are always going to be ones in those spots. And then to build the rest of this triangle, 1 plus 1 added together make that 2. And moving down a row, this 1 plus 2 make that 3. 1 plus 2 make that 3. 1 plus 3 make this 4. 3 plus 3 make this 6. 3 plus 1 make this 4. And so it's a series of adding as you move down the triangle. You won't have to build this. You'll be given this image if you're using the triangle to solve a question, but it's kind of nice to know how to build it in case you ever find yourself in a situation where you don't have it. It's not that hard to build, because if you start building, you're going to have ones on the outside. So you have your ones on the outside. What number goes in here? Well, the 2 numbers that would point to that space, I add those together and put a 2 there. Moving down a row, I'd have a 1 and a 1. The 2 numbers that point to that space, put a 3 there. The 2 numbers that point to that space, put a 3 there. And that's how we keep going down the triangle. 1 and 3 makes 4. 3 and 3 makes 6. 1 and 3 makes 4. And we could keep going and we could build the whole triangle. So that's where the numbers come from. Now, what do we do with these numbers? That's a perfectly reasonable question to ask. When we wrote down the sample space for flipping 3 coins just a few minutes ago, we had something that looked like this. We had heads, heads, heads. We had heads, heads, tails, tails in the middle, tails at the front. Then we had, we had tails, tails, heads, tails, heads, tails, and heads, tails, tails. And then finally we had tails, tails, tails. Everybody okay with that sample space from before, flipping 3 coins? We're flipping 3 coins. So we have kind of 3 things happening here. So what we'll do is we'll go over and we'll look at row 3 of Pascal's triangle. And that's because we're flipping 3 coins. So we look at row 3 of the triangle. And what we see there as our numbers are 1, 3, 3, and 1. 1, 3, 3, and 1. What those numbers correspond to is, how many ways can I get all heads? How many ways can I get 2 heads? How many ways can I get 1 heads? And how many ways can I get no heads? That's what those numbers in row 3 correspond to. I'm going to go ahead and label these. So like over here, this is the number of ways that we could get 3 heads and no tails. This is the number of ways I could get, 2 heads and 1 tail. This is the number of ways that I could get 1 head and 2 tails. And this is the number of ways that I could get 0 heads and 3 tails. Pascal was absolutely a genius. and you list out enough sample spaces and you go, hey, wait a minute. This seems to correlate exactly with the number of outcomes I get when I list out the sample spaces. What Pascal's triangle does for us is it allows us to answer questions involving binomial probability without listing out the sample spaces. Now we can use Pascal's triangle to tell us, well, I know there's going to be 1 way to get 3 heads, no tails, 3 ways to get two heads and one tail, three ways to get one head and two tails, and one way to get no heads and three tails. I guess I could list them, but now I don't have to. Also notice what this does for us is if I want the probability, I need successes and outcomes. Okay, probability of exactly two heads. So I look at my labels here and I say, hey, here's where the two heads are. So I have three successes. Well, that's great, but if I want the probability, I need the number of outcomes. How am I going to get the number of outcomes? This may not be the easiest thing for you to phrase, but I'm going to let you try it anyway. How am I going to get the number of outcomes to go on the bottom here? Outstanding, Carolina. If we add these numbers up, that gives us the total number of outcomes. 1 plus 3 plus 3 plus 1. Because if there's one of these, three of these, three of these, and one of these, that's all my outcomes. So 1 plus 3 is 4, 5, 6, 7, 8. So I can see that the probability is 3 out of 8. And now I can do this without having to list the sample space. I can. If I want to list the sample space, I can. I don't have to anymore because when you tell me I'm going to flip 3 coins, I'm going to go over here and say, all right, well, I'm going to use row 3 of Pascal's triangle. And then I'm going to label these things. That 1 corresponds to the number of ways I can get all heads. This 3 corresponds to 2 heads. This 3 corresponds to 1 heads. And this 1 corresponds to no heads. It's really common for a student to say, well, what if I label it the other way? And that's an excellent question. Like, what if I called this one 3 tails and no heads? And this one 2 tails with 1 head, and this one 1 tails with 3 heads, and this one no tails with 3 heads. Oops, that needs to be a 2 right there, doesn't it? How about 1 tail and 2 heads? And I call this one no tails with 3 heads. And the way that we're labeling these is we have 3, 2, 1, 0. We just go right down the line with one of them. Then the other one's going to be the opposite, 0, 1, 2, 3. The beautiful thing here is this triangle is symmetric. Whatever happens on one side happens on the other. So you're going to get the same answer whether you label it going 3, 2, 1, 0 tails, or if you go 3, 2, 1, 0 heads. You're going to get the same answer either way because it's symmetric. So you don't have to worry about what if I label it wrong, because that's not going to be an issue. I think Pascal's triangle is super cool and gives us a great way to solve problems that involve binomial probability. But I want to make sure that that you understand what's happening. We're going to do one more example before I have you try some of these. Okay. So what if we flip 3 coins? What's the probability of getting at least 2 heads? Here's our approach, just sort of our straightforward, here's how we do a question like this. Because we're flipping coins and there's only 2 outcomes, we know we have binomial probability. That means we're allowed to use Pascal's triangle for this. So what's the probability of getting at least 2 heads? Since I'm flipping 3 coins, I go to row 3 and I find this 1, 3, 3, 1. That's going to be the row that matters to me. Now I want to label my row. And we did it the other way last time. So this time we'll say this is the number of ways to get 3 tails, 2 tails, 1 tail, and no tails. And then just to be complete with my labeling, I'm going to go ahead and put the heads on here too. If I get 3 tails, that means there's no heads. 2 tails means there's 1 heads. 1 tail means there must be 2 heads. And no tails must mean all 3 are heads. So I picked out my row. I've labeled it. What's the probability of at least 2 heads? Well, probability is going to be successes over outcomes. I can add these. 1 plus 3 is 4, 5, 6, 7, 8. So there's going to be 8 outcomes. And now I just need to find my successes. Anything that has at least 2 heads is a success. This is 0 heads, so that's no good. 1 heads, no good. 2 heads, those are successes. And 3 heads, at least 2, yep, that's success also. And so I have 3 plus 1, I have 4 ways that I could get at least 2 heads. So the probability of getting at least 2 heads would be 4 out of 8. Okay, now I want to give you a chance to ask whatever questions you might have, um, because up next, I'm going to have you try a few. Okay, let's try one. A family wants to have 5 children. Having children is boy or girl, so there are 2 outcomes. So this is a situation that involves binomial probability. What's the probability that they have 3 boys and 2 girls? I'm going to set up a poll for this one and let you try it. And this is an exactly, because 3 boys and 2 girls, those are exactly. One thing I will say, having 5 children, so 2 outcomes on the first one, 2 outcomes for the second one, 2 outcomes for the third one, 2 outcomes for the fourth one, 2 outcomes for the fifth one, multiply all those together, this would be a really big sample space that we would not want to write down this entire sample space. And making a tree diagram with 5. So we'd have boy, girl on the first one, then boy, girl coming off of each of those, then boy, girl coming off of each of those. This tree diagram would get unwieldy. This would not be a great spot for that. So instead, because it's binomial, we can use Pascal's triangle to approach this problem instead of a tree diagram or listing the sample space. If you happen to be in the middle of a quiz or an exam and you forget how to use Pascal's triangle, it's okay to use a tree diagram or a sample space, but a little overwhelming when there's this many outcomes. And this is definitely the type of question you can expect to see in homework, on a quiz, on an exam. But you will be given the triangle, so you won't have to recreate it. Let's go another 30 seconds on this and then talk about it. If you want more time, you let me know. All right, let's see how we're doing. Not unanimous, but strong agreement. I can live with that. If you have questions, if you're not sure of where any of these approaches or steps come from, please ask about them. Binomial probability and using Pascal's triangle is typically something that goes extremely well for students, and I want that to be true for you. So if something's happening that you're not sure of why, please make sure you ask about it. So we want the probability of getting 3 boys and 2 girls. They're going to have 5 children, so we're going to go down here to row 5 of our triangle. Easy to identify row 5 because we know we're going to have ones all the way down the outside, and the first number in is a 5. That's row 5. So it's really easy to identify what row you're in by that first number after the 1. If whatever number it is, that's what row you're in. All right, so row 5, and when I go look at the results from row 5, that's 1, 5, 10, 10, 5, 1. One thing I can do right away is I can get my total number of outcomes by adding those together. That'll be, let's see here, 1 plus 5, oops, plus 10, plus 10, plus 5, plus 1, that's 32 outcomes. And the good news, everybody who responded to the poll had 32 outcomes, so that's excellent. So we have 32 outcomes. Another way you could have gotten the 32 outcomes here would have been to say 2 possibilities for the first child, 2 for the second, 2 for the third, 2 for the fourth, 2 for the fifth, and multiply all those together. Still a fundamental principle of counting. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So either way, we land on 32 outcomes. Now we want to go find our successes. And to do that, we're going to label every one of these. What these numbers mean is there's one way to have all boys. That would be 5 boys. And there are 5 ways to have 4 boys, 10 ways to have 3 boys, 10 ways to have 2 boys, 5 ways to have 1 boy, and 1 way to have no boys. And this may be enough labeling for you to answer the question, but for me, I kind of like to label the other thing too, just to make sure. And 5 boys would mean no girls. 4 boys would mean 1 girl, 2 girls, 3 girls, 4 girls, 5 girls. And remember, this number up here at the top represents how many different ways could you get no boys and 5 girls. Well, there's only one way. It would be this. Oops. Nope. It would be this. That's the only way to get girls, is all one girl after the other. And there's only one way to do that, and that's what that 1 represents. The 5 here means there are 5 different ways that you could have 4 girls and 1 boy. If we wanted to list those, and you don't have to do this when you're solving problems, I'm just doing it to illustrate the point that what this 5 represents is you could have 4 girls and the boy at the end. You could have the boy in this position. You could have the boy in this position. You could have the boy in this position, or you could have the boy first. And those are the 5 different ways you could have 1 boy with 4 girls. And that's what those numbers represent. Those numbers make it so we don't have to list them all out. It tells us how many ways it could happen and saves us the trouble of listing them. Okay, let's answer our question here. Question said, what's the probability of 3 boys and 2 girls? So the only successes I have is when there's 3 boys and 2 girls. And now I look and I can see right here is 3 boys and 2 girls. So I have 10 successes in my 32 outcomes. And so the probability of getting 3 boys and 2 girls is 10 out of 32. Any questions on what we did there before we try another? We're gonna, and I'll be 100% honest with you, using Pascal's triangle to answer binomial probability questions, that's what we're doing today. We honestly don't have that much more to cover in section 7.4. I just want to do some more practice. So up next, a family wants to have 4 children. What's the probability of getting at least 1 girl? I'll set up a poll for this and let you try it. just like it was when we were doing tree diagrams. You might be asked for probabilities as fractions. You might be asked for probabilities as decimals. So make sure you can write probabilities either way. We'll go another 30 seconds on this and then talk through it together. All right, let's see where we are on this one. Okay, strong agreement, not unanimous, but I think I know what happened here, so we'll talk through it. You let me know if you don't see why you might not have had the right thing. So a family wants to have 4 children. Children's a binomial event. They're going to have 4, so we're going to look at row 4. And that's going to be 1, 4, 6, 4, 1. And that gives us the number of ways to have each outcome. If I want the total number of outcomes, I need to add these together. 1 and 4 is 5, and 6 makes 11. 4 is 15, and 1 is 16. So there's 16 different outcomes. So we know that's going to go on the bottom of our probability. You could use the fundamental principle of counting to find out there's 16 outcomes here too, if you wanted to. Now we have to figure out where our successes are. And to do that, we're going to put labels on here. Okay, well, let's see. I could say this is, let's see, 4 children. I'm going to say 4 girls, 3 girls, 2 girls, 1 girl, and no girls. Just for completion's sake and just to make sure I'm answering questions correctly, I'm going to go ahead and do, okay, this would mean no boys, 1 boy, 2 boys, 3 boys, and 4 boys. All right, now I'm ready to answer my questions. At least 1 girl. So what I need to do is find the places down here where there's at least 1 girl. Where 4 girls, yes, that's at least 1. 3 girls, yep, that's at least 1. 2 girls, yep, there's at least 1. 1 girl, yep, that's at least 1. And no girls, nope, that one's no good. Just like we did with our tree diagrams. Now I could have a success, at least 1 girl this way, or this way, or this way, or this way. So we're going to add all those successes together. And when we do that, 1 plus 4 is 5, and 6 is 11, and 4 is 15. So we wind up with 15 successes out of 16 outcomes. So the probability of getting at least 1 girl is 15 out of 16. The word at least. Okay, let me back up a minute there, Nicole. Let me back that up just a second. So we're going to go back here. I'm glad I used different colors. That was really good. Okay, so what we're saying here is we're going to have, this family is going to have 4 children. And so what we do is it doesn't matter if you use boys or girls to start with. I chose girls. You could just easily choose boys, and I'll show you how that plays out. But they're going to have 4 children, so we start with the most possible number of girls, which would be 4. And then we reduce that by 1 each time. And what we're saying here, there's only one way to have 4 girls. That would be like that. There's only one way to do it, and that's what that 1 represents. To have 4 girls, there's only one way to do it. As we move along, we reduce this. Now it's 3 girls, And there are 4 different ways where you could have 3 girls, because you could have the 3 girls with a boy at the end. You could have the 3 girls with the boy in here. You could have the boy here, and you could have the boy here. And what we're doing, oh, all right, Lorraine, all right, I'm good with that. That would be just fine. We'll do that next. So my approach is to start with the most and work down. 4 girls, 3 girls, then this is the number of ways to have 2 girls. This is the number of ways to have 1 girl, and this is the number of ways to have no girls. And if I label it that way, and I want to put my boys on there, if they have 4 girls and they have 4 children, then that means they had no boys. If they have 3 girls and they had 4 children, that means they had 1 boy. 2 girls and 2 boys, 1 girl and 3 boys, no girls and 4 boys. Now, Lorraine mentioned she finds it easier to start with 0 and work up. That's absolutely fine. You could do that too. You could say, okay, I'm going to say that there are no girls, and then 1 girl, 2 girls, 3 girls, 4 girls. And that would correspond to, if there's no girls and there's 4 children, then that means there's 4 boys. 1 girl would mean 3 boys. 2 girls would mean 2 boys. 3 girls would mean 1 boy. And 4 girls would mean no boys. Now you might be thinking, those labels are different. Isn't that going to goof you up? And here's the beauty of it. Because the triangle is symmetric, the left half and the right half are the same as each other, these numbers are symmetric. There are 4 ways to have 3 girls and a boy, and it doesn't matter which way you label it. If I label it starting with 4 girls, then I can see in my chart that there are 4 ways to have 3 girls and a boy. If I were to start with no girls, then I can see 3 girls and a boy, there's 4 ways. So either way, you get the exact same numbers. 2 boys and 2 girls, same place. And then 4 girls and no boys, there's only 1 way to do it. And if I labeled it the other way, 4 girls and no boys, there's only 1 way to do it. Oh, gotcha. Okay, very good. Yeah, definitely not random. Definitely not random. We're just, and you can either, you could do it the way that I wrote it down at first by picking one of them and going 4, 3, 2, 1, 0, and then matching up the other one with what it would need to be. Or if you like it better, the way Lorraine suggested, is start with the 0 and go bigger and go 0, 1, 2, 3, 4, and then label the other one to match. We'll do a couple more for practice. Oh, one thing I wanted to make sure I said here with this one is the words at least are very important. When we go to find our successes here, we want anything that has at least 1 girl. There's 4 ways to have exactly 1 girl. But if we want at least 1 girl, then 2 girls is a success, 3 girls is a success, 4 girls is a success. So we want to make sure we count up all of these, and that's how we ended up with 15 successes out of 16 outcomes. All right, let's try a couple more. A coin is to be flipped 6 times. What's the probability of getting exactly 4 heads? Exactly is an important word here. We're flipping a coin 6 times. So we're looking at row 6. I'll set up a poll and let you try it. So be mindful of our process here. Coin's going to be flipped 6 times, so we're looking at row 6. We can add those up to get our number of outcomes. And then when we want our number of successes, we want to make sure we're careful in how we label those numbers. And we want to make sure to identify the ones that are successes. We'll go another 30 seconds and then talk through this one. Okay, let's see how we're doing on this. Okay, very strong agreement. Not unanimous, but definitely strong agreement. That's good. Let me know if you see something that you're not sure of or doesn't make sense. So let's see here. Point is going to be flipped 6 times. So I'm looking at row 6 of my triangle. And that is 1, 6, 15, 20, 15, 6, 1. If I want to know the total number of outcomes, I can add those up. I could also use the fundamental principle of counting and have 2 multiplied by itself 6 times, which is 2 to the 6th. That's another way I could get the total number of outcomes here. If I add all those up, I get 64 total outcomes. All right, now we need to label these and identify our successes. Since this question asked about heads, I'm going to start my labeling with heads. And many of you may feel the same way Lorraine does, so we'll go ahead and start with the 0 and count up. So here I'm going to have 0 heads. This is the number of ways that I can get no heads. That's what that means. And then 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads. This may be all the labeling you need. You may be comfortable at this point. I tend to like to go ahead and complete it and put the tails on there just in case I'm going to get more questions down the road. So 0 heads would mean, well, there were 6 flips, so that would mean 6 tails. 1 heads would mean 5 tails. 2 heads would mean 4 tails. 3, 2, 1, and 0. So now I've got everything labeled. Let me know if there's anything in those labels that doesn't make sense. Now we need to identify our successes. Okay, exactly 4 heads. No more, no less. 4 heads. Well, this is 0, 1, 2, 3. There's 4 heads. There's 15 of those. 5 heads is no good. 6 heads is no good. So that's the only way to get exactly 4 heads are these 15 different outcomes here. Luckily, I didn't have to list all 64 and make a sample space. And now I can see that there are 15 successes out of those 64 outcomes. And so the probability of getting exactly 4 heads is 15 out of 64. Let me know if you have questions on anything we did there and before we try one more. Outstanding. All right. Coin is to be flipped 6 times. Find the probability of getting at least 2 tails. I'll set up a poll for this one and have you try it. We'll go another 30 seconds and then talk about this one. As you can see, really, these questions are very similar to each other. When we have binomial events that only have two outcomes, we can use Pascal's triangle. We just want to make sure to identify the correct row, determine the number of outcomes, determine the number of successes. At least and exactly are different from each other, and that distinction is very important. But this method that we've been using in these problems stays consistent throughout. Let's see where we are on this one. Okay, again, strong agreement, not quite unanimous. If something happens when we go through it that doesn't make sense, you're not sure where the numbers came from, make sure you ask about it. The way that we'll approach this is we'll say, okay, the coin's going to be flipped 6 times, so we need row 6. And that's going to be 1, 6, 15, 20, 15, 6, 1. And we did 6 times last time, so there's going to be 64 outcomes. Now it's just a matter of how many successes there are. You may have just used the labels you had from the last problem, and that's totally fine. But if not, we'll go ahead and label them again. This question happens to be about tails, so I'm going to label using tails. And so there's one way to have no tails, 6 ways to have 1 tails, 2 tails, 3 tails, 4 tails, 5 tails, 6 tails. And just for completeness, I'll put the heads in. This would mean 6 heads, 5 heads, 4 heads, 3 heads, 2 heads, 1 head, and no heads. What you'll notice is this isn't the same labels we had for the last one, but because of the symmetry of this, because we get a mirror image on the 2 sides, that's totally fine. As long as we start at 0 and go up by 1 every time, or start at 6 and go down by 1 every step along the way, our labels are just fine. All right, now it said, what's the probability of getting at least 2 tails? So let's see, here's where 2 tails is. And I need 2 tails or more. So 2 tails or 3 tails, 4 tails, 5 tails, 6 tails. Those are all my successes. So I want to add those together to figure out how many successes I have. And that'll be 15 plus 20 plus 15 plus 6 plus 1. I don't trust myself to do that in my head. So 15 plus 20 plus 15 plus 6 plus 1 is 57. And so what we end up with here is 57 successes, 64 outcomes. So our probability is 57 out of 64. I mentioned earlier that you may be asked to write these as fractions or as decimals. And if we are asked to write this as a decimal, we just divide 57 divided by 64. And let's say rounded to the nearest hundredth, and that would be 0.89. So if we want to write it as a decimal, it's just one more step, divide to get the decimal. Okay, that